So welcome everybody to the fourth webinar series for 2020 for the Blue Economy CRC. I'm John Whittington and I'm the CEO of the Blue Economy, and it's a really exciting time for the Blue Economy CRC. Today's webinar is titled Hydrogen in the Blue Economy, and for the CRC this is a really important part of our work, and we're on the cusp of announcing some really interesting work which will be presented to you today. Before I start, I'd like to acknowledge and pay my respects to the Tasmanian Aboriginal community as the traditional and original owners and continuing custodians of the land that I'm sitting on at least. And I pay my respects to elders past and present and to the many Aboriginal people that did not make elder status, and to the Tasmanian Aboriginal community that continue to care for our country. So the Blue Economy CRC, Leslie, if you just change the slide, has been set up to perform world-class collaborative industry-focused research and training that underpins the growth of the blue economy through increased offshore sustainable agriculture and renewable energy production. And quite clearly, hydrogen fits within our purpose. Leslie? The Blue Economy CRC is made up of 40 participants from around the globe. 10 countries are represented on this slide, and there's a combination of SMEs, large companies, government departments, government research institutes, and universities. I won't read out all of the players, but a number of the companies on there and institutions on there are speaking today. Today we're really fortunate to have a series of excellent speakers. Ian McKinnon, Professor Ian McKinnon from the University of Technology Queensland, is our facilitator and will give a brief overview of renewable energy in Australia. We have Professor Evan Gray from Griffith University, who is one of our co-leads on our offshore renewable energy systems program. Craig Duggan, who's the CEO of the Optimal Group and supplier of great equipment, which we'll be talking about today. Robert Nicholson, Energy Market Lead from Pitt and Sherry, and then Christina Lamb from Griffith University, speaking on some of the work we've been doing on hydrogen storage and distribution. I'll now just hand over to Professor McKinnon, Ian McKinnon. So Ian is a member of our scientific advisory committee to the Blue Economy, and is a fantastic contributor in that space. Professor McKinnon is also currently director of the Centre for Clean Energy Technologies and Practices at QUT, and is an advisor to the Queensland Government on hydrogen. Ian's been involved in a number of CRCs and establishing them and being on boards, and I really welcome you, Ian, today, and I'll throw to you.
Thank you very much, John. Indeed, a very exciting lineup of 4 speakers today, and looking forward to hear from them all. Just a few moments to spend here on housekeeping. I'd just like to make sure that all attendees can, in order to see both the presenter and their slides, could you please ensure that your screen is on speaker view at the top right-hand corner of your screen. We encourage you to use the Q&A function during the webinar, and the speakers will be able to answer any questions at the nominated Q&A time a bit later on. With one exception, Robert Nicholson will have a bit of a question and answer session straight after his presentation. And attendees are able to upvote questions in the Q&A, so the most popular questions clearly get a lot of attention. So please only use the chat if you're experiencing technical issues or you have a direct question that's important to of importance to one of the panelists, and one that you don't need to include or don't wish to include in the Q&A discussion. And note, as I mentioned, that Robert Nicholson departs early at 4 p.m, so we'll have a great Q&A with him at the time. Now, I'll just look to ensure that, make sure that our speakers are aware that we'll be keeping a close eye on them, and that we expect to be able to finish up at around about 4:30 this afternoon in standard Eastern Australian time. I'll now look to share my screen so that we can get underway. Yes, should be there. Okay. So I'd just like to give a few brief comments about the state of renewable energy in Australia and the revolution that's actually going on at the moment and has been going on now for quite some time. And we can actually track it back quite a few years. And its relevance, of course, to the Blue Economy CRC is that very much part of this particular CRC is an understanding of how renewable energy plays a part in developing and meeting the objectives and goals of that CRC. Basic energy statistics here just in front of you right now. You can see that we're still clearly a major exporter of LNG, but down here in the left-hand corner, you'll see that the growth in solar generation in the period 2018 to 2019 is up 50%, substantial. And the other thing that's important to note about the energy industry is that electricity is seen as the predominant vector that will be occurring for energy generation use in the future, at least till 2050. And our electricity generation from coal is down and dropped substantially down to about 56% at the moment. You can see here also that renewable energy has had a significant role in this change of both our energy consumption and our energy intensity. And if you look over on the right-hand side of this particular slide, you'll see that of the renewable energy profile from 1993, which was predominantly hydro and mostly out of Tasmania and the Snowy Mountains, we can see now that we've added to that wind energy, bioenergy and solar. And not surprisingly, an important factor here is the position where ARENA started around about 2012. And you can see as a result of its engagement with the community in many different ways, that both wind and solar in particular have taken a substantial increase over the past few years. This is rather good news, and you can see here that the total amount of investments in renewable energy across Australia, this is from a clean energy report just recently presented in April of this year, that there's a substantial amount of investment in renewable energy across all states, and in the order of 14,000 jobs being put in place over that period or transferred from other roles within other industries. As you can see on the right-hand side of the slide, Tasmania is substantially already a renewable energy provider. And interestingly, will probably be an even greater renewable energy provider in the future based on the announcements recently made by the Premier of Tasmania, where it aims to be in the order of 200%, that is exporting renewable energy from the state by 2035, I believe it is. But the point about this is that our renewable energy capacity now has grown to around about 24% of the total energy capacity in Australia. And that's a substantial increase from previous years. And at the moment, the split is roughly 36 or 37% solar, 33% wind, and the rest of it 31 or 32% hydro. 2 or 3 years ago, hydro was the dominant mode of renewable energy. And so solar and wind have certainly taken an increase over the past few years. And it's predicted, of course, that there'll be a large amount of renewable energy required by 2040 in the order of 30 to 40 gigawatts of capacity by that period. And this is a prediction from AEMO, the operator of the national grid in the country. So that's all looking good. And if you look at the other part of this slide, you'll see that the solar PV uptake or revolution was originally consumer driven. In fact, many households, due to a good policy, put solar panels onto their houses for long periods of time. It was only after this period, 2013, 2014, that large-scale solar farms started to be put in place. So it's an example of how Australians in general will use their hip pocket to drive technologies in different parts of their economy. Finally, I just want to point out that as part of this exercise and letting people know about what's going on in different parts of our renewable energy sector, a very important resource that's just recently come into play has been a site called High Resource, which has been co-supported by CSIRO and the Hydrogen Council. And it's an excellent location to go to look at what's actually happening. It's a live site. It will be updated on a regular basis and is a good resource for people if they want to find out more about what's happening in the specific area of storage or energy storage using hydrogen. And finally, I'll just now start to turn over to our speakers, because really just wanted to give you a flavour that renewable energy is a very, very important part of Australia's economy nowadays, and is a very good basis from which we can then start to look at transforming many of our other industries that utilise energy in many different ways. So I'll now release my sharing of screen, and I'd like to introduce Professor excuse me, Professor Evan Gray from Griffith University, who will be speaking about hydrogen in the blue economy. Evan is a professor of physics at Griffith University, predominantly spent a lot of time working on solid state physics, in particular methods of storing hydrogen using solid materials, and his expertise both in pure based physics, modeling of processes related to renewable energy, and of course to his broader understanding of the importance of storage in our electricity grids is unparalleled. He was also a very important person in the development of the very first microgrid, hydrogen-based microgrid at 2 megawatt hour capacity installed at Griffith University back in 2013. So I hand over to you, and Evan, underway.
Thank you, Ian. Good afternoon, everybody, or good whichever part of the day it is in where you're joining us from. Evan Gray. I'll move straight on to talk about some aspects of hydrogen in the Blue Economy CRC. And first of all, I'll talk about the milestones. These are goals agreed with the Commonwealth as part of our funding package. And some of these relate very specifically to hydrogen. There are the word hydrogen occurs in a number of places in connection with offshore renewable energy. So that includes hydrogen production and storage and end use. And hydrogen microgrids feature largely, and also the possibility of using fuel cells to replace diesel generators for vessels, probably not very large ones, but vessels are in there, and also various kinds of drones. And as Ian mentioned, modelling is very important here, because until you've modelled such a system, you don't really have any idea of how it's going to behave. So some properties of hydrogen, first of all. Hydrogen is very light, has a low molecular weight. That means it's difficult to liquefy. It doesn't liquefy until minus 253 degrees centigrade. And that means its density under ordinary conditions is very low. And that just means it's very hard to store. So this is a universal problem with hydrogen that will never go away. It's in the nature of the beast. One of the things about that, however, is that because it's light, it diffuses very fast. So if you have a leak, it's gone quickly, unless you confine it when you can make it explode. It's harder to do than people think. The energy density by weight is superb, and the energy density by volume is terrible. So that's a kind of a summary of the problem of using and distributing hydrogen. And I'll just point out over here, one of the interesting things about hydrogen is that the flame of burning hydrogen has a very low luminosity, so there's not much radiant heat. You can be very near a hydrogen flame but not actually feel the heat. So that's one of the safer things about it. Okay, everybody wants to know about this. Everybody's heard of the Hindenburg disaster, and therefore they worry about hydrogen. So here is the Hindenburg in flames in 1937 as it came into land in New Jersey. And yes, quite a few people were killed in the disaster, but you'll notice there's no explosion. This is burning, and it's actually the skin of the airship burning because it was made of a flammable material. Helium-fueled airships also burned. The skin's the problem, not the hydrogen. Yes, it burned, but the problem was the skin. We're used to fuels that are a lot worse than this. This is an LPG fire on a freeway. And here's a comparison between fires in a petrol engined and fueled vehicle at the same time as a fire in a hydrogen tank in the same vehicle. And it's obvious which vehicle you would prefer to be in. Okay, so hydrogen at present mainly comes from fossil fuels, mostly by steam reforming of fossil fuels, especially natural gas. So in order to have clean hydrogen, we need to have a clean source. So we need to either capture the CO2, and there are plenty of projects talking about doing that, although the scale at which it has to be done is fairly terrifying. Or at present, the practical route to clean hydrogen that everybody can do is by electrolysis. That really only accounts for a very small fraction of the amount produced at the minute. So the hydrogen supply needs to be cleaned up in order for this clean energy vector to actually be a clean energy vector. So that's green hydrogen we're talking about. Grey hydrogen is hydrogen produced from fossil fuels and the CO2 is liberated, and blue hydrogen is with CO2 capture. Most of the hydrogen that's presently produced goes into feedstocks for industry. Here, of course, we're talking about hydrogen for energy mainly. So the hydrogen supply chain consists of a number of steps where you can produce hydrogen, I'm assuming by electrolysis at the minute. Here's an example of a platform at sea connected to offshore wind. And the end use at the minute, we're looking at very early stage vessels, land transport, of course, but the context here is maritime hydrogen. And in between, we have some fairly sticky problems to do with how you store hydrogen and how you distribute it. And the same modalities are available to do each of these things. Gas is difficult because of the low density of hydrogen. It has to be compressed. So to supply light-duty fuel cell vehicles, 70 megapascals or 700 atmospheres is used, 35 megapascals for buses and heavy vehicles, and perhaps lower than that for marine vessels. Liquid hydrogen, 20 Kelvin, problematic. Solid state hydrogen, practical and commercially available, but very, very heavy. And so-called chemical routes, including ammonia, that's a very likely modality for export from Australia, and liquid organic hydrogen carriers like methyl cyclohexane toluene, and as I said, ammonia. These are all possible routes for storing hydrogen. They're all possible routes for distributing hydrogen, and different modalities have different applicability for storage and distribution. So these are areas of very, very active research and development at the minute. Just a quick tour through some projects going on around the world. This list is by no means exhaustive, and I must thank Mark Hemer, the leader of Program 3 in the in the Blue Economy CRC, the program in which I'm the deputy leader. I must thank Mark for passing this list to me this morning, saving me a lot of time. So this is not exhaustive, and it's somewhat Eurocentric, but that's for the reason that there are many projects going on in Europe. And I'll just point to a couple in this and the next slide, just to show how fast things are going. This one here, the North H2 project, is now talking gigawatts on the time scale of the next few years, and here it is in cartoon form, linking a number of sites in Europe and employing offshore electricity generated by offshore wind to produce hydrogen by electrolysis. So this is a very large project, and there are numerous others. Vessels looking interesting. As of I think 2 days ago, this project was announced. This is a very serious vessel indeed, this ferry to run between Denmark and Sweden, I think, I now forget, but in Scandinavia. And there are some other smaller ones here that have been developed over the past few years. And these are not, they're only small compared to this huge thing. These are significant projects. And there's a lot of work going on, not actually producing devices or processes, but in studies into important matters such as de-risking hydrogen infrastructure. These are very, very important projects. So there's a huge amount going on around the world at the minute. It's a very exciting time to be involved. In the Australian context, we lag in terms of the scale of projects and the state of advancement of projects. I'll just mention this elephant in the room over here, which is the Star of the South project. On their website and in the documentation about the project, the word hydrogen does not occur, but some of the electricity that arrives over here in Victoria could well be used for generating hydrogen, but it's not part of the proposal for the Star of the South project, and that's why it isn't included in my list. So there are plenty of opportunities for us, and the Blue Economy CRC is interested in quite a few of these. I won't read them out, you can read them for yourselves, but plenty of opportunities, as I say, in Australia for exciting projects connected to the maritime environment. My last slide is about the demonstration project, which has now been agreed and will be going ahead next year. Craig Duggan from Optimal will be talking about this more in his presentation in a minute. Phase 1 has been agreed, going ahead next year. This will consist of a 690 kilowatt electrolyser for producing hydrogen and a capstone turbine for generating electricity from hydrogen. This is demonstration scale, but still significant demonstration scale, with offtake of oxygen and hydrogen, and a DC microgrid connecting these components of the system together. Hopefully we'll be able to add some offshore renewable energy conversion to the system, and we will need other stuff in there. We'll be powering the electrolyser on green electrons from the external grid, but in phase 2, this system will be replicated offshore, so it'll be split, and then in phase 3, the whole thing will move offshore. So this is a really exciting project we're looking forward to getting on with. And with that, thank you for your attention.
Thank you very much, Evan. Most appreciated. Excellent summary of the activities that are not only going on around the world, but also delivering and beginning to start to be delivered in the blue economy in Australia. Our next speaker is Craig Dugan. Craig is CEO of the Optimal Group, and he has a length of experience, 30 years in the oil and gas industry and the energy industry in general, and a chemical engineer. He's become a very important member of the Optimal team, providing solutions to both the Australian and South Pacific markets across a wide range of energy activities. I'd like to now hand over to Craig and and have him take over the presentation from here. Thank you very much.
Good afternoon, everybody. I trust that everyone can see my screen. I'm sure somebody will wave frantically at me if you can't. So Evan has introduced, I guess, this question of our project, and I just want to sort of take a couple of steps back and say, well, you know, what drives all this? And our business is we're in the lower carbon power business. So our customers are a range of commercial and industrial customers, but they have one thing in common, or two things in common. They want to reduce their cost of energy and they want to reduce their emissions. And so what's driving this? Obviously climate change. And the good news is that we're now seeing a lot more cultural, a lot more community engagement and pushing governments on that climate change issue, which is leading to opportunities. And just to help frame out what this looks like. So this little pie chart here shows the European energy picture, and you can see there that the little pizza wedge, if you like, that's the electricity requirement for Europe. Now this obviously includes transport, but the far larger part of that is the molecules part of their heat requirement. And so if you then think about what we need to do if we're greening our networks or if we're greening offshore renewable systems, it's a major problem. You can see here, this is the Melbourne's electricity grid between 2015 and 2025, and progressively our grids are becoming overloaded. And this is not a Melbourne-based problem, it's an Australian problem, it's a worldwide problem. And so the problem that we then face is that everyone complains about the cost of energy. And if we then think about the context of industrial customers, large-scale food manufacturers who want to reduce their CO2 footprint. In fact, they want to go to net zero. But if only 25% of their energy need is electrical, how the hell do they do that? How do they get rid of their heat requirement? They can't simply put all of that energy, that additional energy, into electricity and pull it from the grid, because the grid doesn't have the capacity. So we can look here and we can see Melbourne's high-pressure natural gas networks, and coincidentally, the high-pressure gas networks go exactly where our electricity networks go. So if we could only turn those gas networks into green energy networks, then maybe we could do something. And I guess the point is that it's got to be more. We need more than cables if we really want to decarbonize our societies. Then gas or renewable gas needs to be a part of that. So you might say, well, hang on, why don't we use storage? And so, flywheels have been around for a long time. Batteries, has been an enormous advancement in batteries, and certainly batteries will continue to get more efficient and lower cost, and I expect they will move up that curve. There's other forms of storage, probably not well known. Compressed air, that can be where you pump air down into the ground and then pull it back out, expand it to make power. Or pump storage. So everyone's heard about Snowy 2.0. So literally pumping water back up into hydroelectric dams with renewable energy and then pulling it back down again. But what you can see here is that hydrogen is a very cost-effective way to store large amounts of energy. And so that's what we're going to sort of focus on today. So how do we do it? So in simple terms, you use electrolysis, and electrolysis is a process by where you introduce a DC current into water, and you split the water molecule into its constituent elements of oxygen and hydrogen. So you O2, which is the air we breathe, the oxygen in the air that we breathe, and hydrogen. And that electrolysis process is now well and truly proven, and there's a reasonable number of manufacturers worldwide who have packaged these systems up. Interestingly, this whole process is in fact quite old, and the original Apollo spacecraft ran on fuel cells, and that hydrogen could have been produced via electrolysis, or maybe it was from a refinery source. So to produce that hydrogen, you want to use renewable energy. And the beauty about that is that, and we heard earlier on about the large amounts of renewable energy that are being installed. What happens when we do that is we then end up times with surplus renewable energy, and that's an ideal opportunity for an electrolyzer to suck in that surplus renewable energy, turn it into hydrogen, store it, and then use it when energy is a premium. And so you can use the grid, you can use our electricity grid to feed that electrolyzer, or you can use a local renewable energy source. And then that hydrogen can go to a million different uses: fuel for trucks, cars, buses, trains, and I think ultimately aeroplanes. You can go back to power through fuel cells or gas turbines. It can be used as a feedstock in the chemical industry. It can be used to make ammonia and then ship the ammonia, transport the ammonia effectively as a means or a vector to transport hydrogen. So there's a whole variety of uses for that hydrogen. So then let's go back to the real world, and this is a project that we're actually doing right now. So this is a good example of how hydrogen can go from being a theoretical vector, if you like, energy vector, to a real vector. So McCain's Foods, everyone knows McCain's. They are one of the largest producers of potato chips in the world. And we're at the moment in this middle section here, we're producing, we're putting two 800 kilowatt capstone microgas turbines that are going to be running on biogas. The biogas comes from 200 tonnes a day of potato waste. They process 600 tonnes. There's 200 tonnes a day of waste. It's mostly starch, perfect for making biogas through an anaerobic digester. We use that to power our turbines. We then use the hot air exhaust from our turbines to hot air fire their boiler. Their boiler is a 25 megawatt high pressure steam boiler. Their electrical load on site is about 8 megawatts. So you can see, like we talked about earlier on, larger thermal load than electrical load. By co-firing with hot air like that, we take about a 3 megawatt load off that boiler, and we therefore reduce their carbon emissions from that boiler. But then how do we go further? So here's how we go further. We put in an electrolyser on that site, and we use renewable energy from the grid, or maybe some surplus renewable energy from our system, and we use that to make hydrogen. That hydrogen can then go into the boiler and be blended into natural gas to further reduce the CO2 emissions from that boiler. Any surplus hydrogen can go into the local energy network, and in that particular case, we're looking to fuel buses and garbage trucks. And interestingly, I spoke earlier on about surplus renewable power. We've been able to access a very low-cost grid-based green PPA to provide the majority of the electricity for that electrolyser. So the electrolyser is making green hydrogen from green grid electricity. The oxygen from that electrolyser, it just so happens by a lovely coincidence that there's a large wastewater treatment plant next to the McCain's facility. Over 50% of the energy for that wastewater treatment plant is in aeration of their aerobic ponds. So if we push the oxygen across to that sewage treatment plant, we can reduce their energy consumption by up to 50%, or their electricity consumption by up to 50%. So suddenly, with biomethane and with hydrogen, we've reduced the customer's carbon footprint substantially. We've reduced their energy costs, and we've got these flow-on benefits to these other third-party users. And this is something that we're going to see more of, these sorts of co-located projects. I've got some ITM slides here that just show a project that they've done in Scotland, the Orkney Islands, and so it's a bigger example of using multiple connected renewable energy sources and then surplus energy to make hydrogen, and that hydrogen is then used in fuel cells at a marina. It's used for heating schools, etc., etc. They're using, and in particular in this case, they've also got wave energy as a part of the renewable energy source. And you can see on the left-hand side of the screen there, they've sort of made up this microgrid, if you like. And what that also, by having the electrolyser there, the electrolyser performs another interesting function in that it can soak up very quickly surplus electrons when they're there, or it can drop load off. And this is what they call FCAS, or frequency response. So the electrolyser actually is providing additional grid stability services as well as the hydrogen storage. This can be done at a very large scale on our large metropolitan electricity networks in exactly the same way. So I used the term microgrids before, and the microgrids are going to be really important both in an onshore and an offshore environment. We're in the process of doing some work for the Australian military. They want to reduce their carbon emissions. So here we've got an example of a microgrid where you've got a DC cable which connects multiple both sources and sinks for power. So we've got turbines or fuel cells or batteries as providing energy to that network, and then you've got the army plugging in hybrid vehicles or whatever, taking energy off that network. And so and if you go back to what the ITM did in Orkney Islands, they did basically the same thing across those multiple islands. And so in the blue economy context, we're looking to do exactly the same thing, to move offshore, to have a variety of renewable energy sources offshore, so wind, wave, solar, tidal, and then if you can't use all that energy at the particular time, you go through an electrolyser and you store that hydrogen, and then you can pull it back into that system as you require. So clearly, if you do that, you're going to have excess hydrogen. And so what might you do that? Well, we're going to obviously use it for vehicle transports, and hydrogen, I think, has a very, very good capabilities in vehicles, in buses, and ships. And I think we'll also ultimately see it going into aircraft, and this is a slide from Boeing. So I think I'm probably out of time, am I, Leslie? So I'm going to just stop it there. This presentation will be on the internet, so you can have a look at it at your leisure. But it gives you an example of some of the things where hydrogen can move into our existing energy economies. Thank you.
Thank you very much, Craig. Very nice overview and giving some very good details on explicit projects that have been carried out in other parts of the world, and where I'm hoping we can do the same thing in Australia. Very well. Now, our next speaker is Robert Nicholson. Robert is from Pitt and Sherry, and he has, again, many years experience in this world of energy and energy transformation. And I guess I'd like to just hand over straight to Robert so that we can get some questions in there for you at the end of your talk. Robert, away you go.
Great. You can see the screen there?
Yes, thank you.
Yeah, great. All right. Just a little bit of blurb, I guess, about Pitt and Sherry. We're an Australian-owned, employee-owned engineering business. We've got 7 offices across the country, been around since about 1963. So we like to play, I guess, in manufacturing, energy, infrastructure, mining, and public utility space. That's primarily where we deliver our services too. So a little bit about us. Just wanted to go back perhaps 146 years or so, and this chap Jules Verne, he sort of came up with this fundamentally science fiction philosophy, I guess, that one day hydrogen or water, in fact, or the constituents of water, hydrogen and oxygen, will be an energy source. And I think if we go back to then, when he was writing a sort of a fiction novel, we fast forward to 2020, and there's quite a lot of people who still think it's science fiction, unfortunately, but there are also a lot that don't. The approach of how we make it and what the energy sources out of water are might be slightly different to what Jules Verne had sort of pondered back then. But really, the hydrogen economy is gaining a great deal of acceptance, and the industry is looking really hard to see how it can identify and realise specific value out of that. I'm going to talk a little bit about some of the value chains today on hydrogen, and Craig has mentioned a few, and so has Evan. So it'll just be more sort of a specific case example, I guess, of what they might look like. The opportunity for Australia, though, as the others have already mentioned, is significant. Deloitte says it's going to be worth $26 billion in 30 years' time and create 17,000 new jobs. Well, the rapid advancement or the pace of how it's going could well see that exceeded. This is a slide of a year ago, or from a report of a year ago. We all know that it's just been in every news feed pretty much that we see across the social media and different things. The networks, gas and electricity systems, it's very prevalent there. Transport has been talked about. The export, the magic $2 price. Is it going to reach that by 2030 or earlier? And then there's the industrial processes as well. Craig talked a little bit about just how hydrogen is made. I just like having a little animated graphic in a PowerPoint presentation, but this is quite a good one. Renewable energy through electrolysis, and renewable energy and water through electrolysis, you produce hydrogen. And whether it's used in a fuel cell like this or for other purposes, then stored or directly used in a turbine or some other thing. There's a range of different services that it can be applied to. So, I think just looking at a specific example of what those value chains are, because it shows hydrogen here, and there's a couple of plugs in those boxes that aren't connected to anything, and there's you know, there's oxygen that Craig talked about. There's also the heat and so forth that might come off some of these processes, and so they can be significant value adds to anybody's project. What is the value at the moment? Well, I won't go through all these again, but there's the ones in black are the things that, you know, get talked about a lot, as well as the refueling for fleet and buses. But fundamentally, you know, a lot of these projects are starting to happen around Australia. Ammonia is being produced, or feasibilities for ammonia production, large ammonia production in WA and now in Tasmania again. The ones that probably don't get talked about very much, and Craig touched on, is the use of oxygen and the use of heat from the electrolyzer process, or beyond that at a turbine process. The ones in black, you know, they're going to be fairly big, large scale projects, probably centralized, having a fairly significant impact. But you know, refueling can be something that happens on site, on demand. It can be a decentralized facility, and it really helps establish some of the domestic market. And I think it's generally accepted that domestic market needs to be developed alongside an export market in Australia for it to be, you know, viable and the uptake to be accepted and people to adopt it. So those waste products, what we consider to be waste products, perhaps from the manufacture of hydrogen, and it is effectively a manufactured product, you know, can become quite important. So a couple of years ago, we did or probably it started just over a year ago. In fact, it seems like a couple of years ago with the way this year's gone. A feasibility study at a wastewater treatment plant, and we looked at a number of different things in that plant. And why we used a wastewater treatment plant was effectively it's got a fairly critical ingredient for making hydrogen, that's water. So here's a plant that has a service population of about 38,000, decent water inflows of 7.2 megalitres a day, similar outflows, existing energy consumption of about 2 gigawatt hours a year. Now we're paying around 10 cents, so pretty good. We put in we proposed in this study a 2 megawatt electrolyzer, which will give you about 33.5 or so kilograms of hydrogen an hour, so enough perhaps to fill a bus, a little bit less than filling a bus. And we ran and we modelled that electrolyzer at about a 95% capacity factor. And there was a few things that we looked at in order to get to that point. Initially, we started with a large behind-the-meter solar system, but then the land was not great use and it was used for other things. A behind-the-meter only system, excuse me, allows you for a very short capacity factor of the electrolyzer, so then it pushes up the costs and things like that, and you end up, you know, getting very expensive product because you still spending the same amount of capital. We went to the PPA market, and then we're able to source effectively, and similar to what Craig was saying, you know, large quantities of very cheap energy over the wire. And that allowed us to run the electrolyzer at a much greater capacity. In fact, you know, 95% almost continuously. Electrolyzers can ramp up and down very, very easily. We understood quite well the flows within the wastewater treatment plant and so forth. We had a commitment to use the hydrogen as an offtake, and we wanted to specifically say, well, what is the value of oxygen to the wastewater treatment plant, and using that in the oxidation ditch in the aeration process. And we also looked at the heat that was going to be available, and you know, there was a range of different reasons why we didn't end up using the heat. But you know, the sum up of this was we ended up with about 277 tons of hydrogen a year at a very reasonable levelized cost. And this will continue to come down as energy inputs come down, as the electrolyzer costs and things come down. So, you know, it's going to be one of those things that, I don't know if you can see that, sorry, that continues to decrease in its levelized cost. Craig mentioned that the impact on the blowers and the aeration process. We put into this feasibility study after a lot of research, and we felt we were quite conservative. There would be a 30% benefit to the wastewater treatment plant through that delivery of the oxygen to the blowers, and the blowers were, you know, over 50% of the energy consumption. So having that, you know, that impact was quite significant. And on top of that, and it was something that we sort of discovered as we went along, was the reduction in sludge at the end, and which meant a fairly significant reduction in haulage costs for this particular plant, of around about 30% per annum. Yes. So, you know, we ended up giving the oxygen a value, even though we weren't looking to sell the oxygen at all. This is not a case of about how much is the oxygen worth per se. It's about how can we improve the value of this project by utilizing effectively waste streams. You can extract heat off the electrolyzer. It's fairly low grade heat at around sort of 60 to 80 degrees. We also looked and ran some modeling on forfeiting some of the hydrogen that we would produce to run a turbine to create electricity, and higher grade heat, heat of, you know, sort of 300 degrees, and use that in the sludge drying process. And this particular site just meant that wasn't it was more logistics than anything else why that wasn't used. And of course there was a fairly significant increase in capital, not for those particular pieces of equipment, but for further drying. Very strong NPV and a very attractive discounted payback. So, you know, we were fairly happy about how this panned out and how we could actually increase some of that value out of making the hydrogen itself. We knew we were going to sell it. That wasn't a big issue. It was what to do with these other things and how we could get additional value to that business. So we've, you know, if we look at some of those things, with utilization of the exhaust oxygen is a big deal. You know, the recovered heat from the electrolyzer process can be a big deal. The electricity generation through fuel cells and or through electricity and heat with a gas turbine, you know, has a big impact. As the price of hydrogen goes down, you know, the value of these waste products actually becomes more important, because then it really does drive an attractive business proposition. So, you know, Craig's company provides a number of different turbines that can be, you know, very well suited for this type of thing. We were looking at a direct exhaust, direct drying facility that in this particular case, but, you know, they can be looked at for providing a range of different things, process heat, for cooling through absorption chilling. You know, there's a range of different things. And in the case of, you know, the blue economy, these are the sorts of things that we want to look at to see how these additional values can be captured. Oxygen on its own in the aquaculture industry, you know, it's been suggested that it has a significant benefit, and there's a list of a number of them here. You know, optimum growth rates for the fish, for lower mortality, higher sales price, a whole range of things, pumping cost savings. You know, this is from industry. The industry articles and magazines continue to appear to support it as well. So, and this is obviously, you know, where the blue economy will better define some of these metrics and understand more thoroughly exactly what the benefit is. The application of heat obviously is also going to have several applications in offshore platforms, and it's certainly, you know, in the sort of southern oceans. I won't go into these. These have all been talked about. The possible the exception of this renewable methanol plant, which is feasibility was just granted for that a couple of weeks ago in Tasmania, that we're involved with, and that was part of Tasmania's drive to increase the production and industry of hydrogen. It'll be quite interesting, but these other things are, you know, they're out and about in the world already. Both Evan and Craig have mentioned those. So, you know, perhaps, you know, this could have been Jules Verne's motto, right? Inspired thinking. It's our vision statement at our business, and so that's why this sort of thing is really quite interesting and exciting. So we're looking forward to what comes of the work at the Blue Economy, but also in the industry in general. And that's my wrap.
Thank you very much, Robert. We have just a few minutes to answer some questions. I'm just looking at them. There's a few questions here for Robert. Just trying to find a very good one. It's more of a statement, but has the pun 20,000 leads under the CRC been used yet? And I think anyone can answer that question.
Check with John.
So I guess the question from Peter Jolly here, did you take account of maintenance and what's the MTBF of an electrolyzer? Do you have any response to that, Robert?
We did look. We looked at the life cycle across all the equipment that we were putting in. We ran it in conjunction with the client's financial system as well, and things like finance costs. We're going to replace the electrolyzer after a certain period of time. So we tried to account for as much as possible. We talked about service level agreements with the providers of the equipment to make sure that there was support, that this wasn't something that was going to be dumped upon a utility or a council or someone to say, here you go, this is a great thing.
Yeah.
And there was a range of different, you know, it included civil engineering, it included, you know, the tube trailers to pick it up and take it away and schedule all that sort of thing. So yeah, it was tried to be as thorough as possible.
Got another one for you from Werner. What would be your achieved costs for electricity out of process heat, and what technologies are you using here? I think in your case, you actually said you didn't look at process heat for the wastewater treatment plant.
No, we didn't. I mean, we looked at the quantity of energy we could capture on that and its equivalent. So then you could just say, okay, well, if there's this many gigawatts of energy available, then how much is that going to cost? It wasn't quite as simple as that, because it was comparing it to their existing process of dewatering the sludge, and really it was basically space available. But the bigger picture of that is that you might have one large central site that other sites can then deliver a process to, and you reduce a whole range of trucking, because a lot of the sites will truck it off and
that's right,
take it to someone else's jurisdiction.
So there's a level of saving from reducing the trucking costs, basically.
Yes, there is. Yeah.
Another question from Jonathan. Whoops, I've just lost it. Something about the ramp rate of electrolyzers. You're saying that they can have some flexibility. 0 to what, 50% in what period of time? Any idea?
You'd have to go. I don't want to get the sort of the technical specifications wrong, but they ramp up. They generally a minimum of about 20%. They almost run like a variable speed or frequency drive, but 20% to 100%, they can get to 100% very, very quickly. And that's just why, you know, Craig's talking about the whole FCAS opportunities and you know, good stabilization. It's very, very quick. So but importantly though, you can, if you were running it purely off behind the meter renewable, if you wanted to run it at a fairly low capacity, then you can have it starting, you know, before the sun is completely maximising your plant. So you can start a little bit low and start producing straight away.
Okay, got it. Yeah. All right. Well, I think that's very good, Robert. I think we're pretty much on time. We've got about slightly over time now, so might like to take the opportunity now to move on to the next speaker, if we can.
Thanks.
Next speaker is Christina Lamb. And Christina is from Griffith University, leader in the renewable energy and hydrogen energy technology research, and works currently at the National Hydrogen Materials Reference Facility at Griffith University. She's had quite a lot of time in fuel cell technology, doing a PhD in that area, and has worked for CSIRO over the past few years, and is now also including in that Women in Engineering invited guest speaker, and is now working at Griffith University in this area. So I'd like to now hand over to Christina to get underway. Thank you.
Thank you very much, Ian. I'll just share my presentation. Share screen and then share presentation. Sorry everyone for the picture inception. How are we? Okay. Okay, hopefully you can all just see my presentation. So thank you very much everyone for coming online today. Sorry, I'm having some trouble with, there we go. Okay, at the beginning. So thank you very much. I'm going to give a brief, very brief summary of our scoping study on hydrogen storage and distribution methods. So we wanted to, with this study, wanted to address kind of a balance between the broad technical assessment and the in-depth industrial and literature experimental reporting. In comparison to, there's been a number of reports and studies and things like the CSIRO hydrogen roadmap and other reports that were very broad in their assessment of the hydrogen energy, the hydrogen energy mode, So specifically, we were focusing just on hydrogen storage and transport energetics using known transport methods, so trucks, trains, boats, so no consideration of novel transport methods of air or undersea, and we didn't look at pipelines at all. And this report also does not include any analytics or discussion of the hydrogen production or use technologies, except in the economic assessment where we assume 55 kilowatt hours per kilogram of hydrogen, and that fuel cells are 50% efficient of the lower heating value of hydrogen of 33.3 kilowatt hours per kilogram. So the methods and the assumptions in the report were that we used literature survey to extract process and energy costs. So all of the values came from literature. We didn't calculate any of them ourselves. The energy calculations were made generally using best case scenarios and industry expected efficiencies. All literature values were converted into kilowatt hours per kilogram. So everything is in kilowatt hours per kilogram, except for some of the economic stuff. And the assumption is that each process is hydrogen in and hydrogen out, and high purity hydrogen at 20 bar. So that means that every process is assumed to have the same input and the same output. The number of hydrogens in and out changes slightly in the economic assessment, but the process is the same. We also haven't included in any of the costs or any of the energy costs, the initial systems, the initial processing of imported materials, labor, insurance, costs of equipment, etc. And no heat recovery is assumed in most of the processes. So this is really quite a raw assessment of just the energetics of the processes. So we did an assessment of initially 21 storage methods. So here is the summary in very small text, so hopefully you can all see it. So there's we divided up it into categories based on the residues or the things that needed to be either released or returned for storage. So with pure hydrogen in gas and liquid hydrogen, you don't have any residues. You've just got a tank, and when it's empty, it's empty. On the hydrogen carriers chemical, they have nitrogen or water or carbon dioxide or carbon monoxide released upon decomposition. So most of them are gas and liquid or water. So that means that you can essentially release them to the atmosphere and not worry about it too much. And the reversible carriers all require that you have something that's generally heavy or quite large that has to be returned for refilling. Just a note here, none of this analysis assumes that you're going to on-sell any of the other compounds. So that's things like with the methyl cyclohexane toluene cycle, we're assuming that you're going to return the toluene to be rehydrogenated into methyl cyclohexane rather than selling the toluene as a secondary product. So of those different technologies, we looked at the 4 here that are actually have the highest technological readiness and commercial readiness of each of the types of technologies. So there's the gas, hydrogen, ammonia, which is chemical storage, lanthanum nickel 5 is a solid state reversible storage, and the methyl cyclohexane toluene cycle is a reversible liquid organic storage or reversible liquid organic hydrocarbon, depending on what you'd like to call it. And then across the synthesis, storage, large-scale storage, transport by pipelines, by trains, by sea, by whatever, and also the reversible or the reversal technologies. We looked at the commercial readiness and technological readiness of all of these and of all the different steps. And you can see that only gas phase hydrogen of these 4, which are the best of the technologies at the moment, actually has commercial and technological readiness across the value chain or across the chain. Even ammonia, which is the next in the storage, has quite low commercial readiness of the decomposition processes or the reversal processes. And the things like lanthanum nickel 5 and methyl cyclohexane, sorry, I'm just going to call it MCH from now on, will have quite low technological readinesses, and some of them don't even have, quite low commercial readiness, and some don't even have very high technological readiness. So there's still more research that needs to be done to really develop those technologies. So moving on into the technical summary, this graph or plot represents the energy investment for each of the technologies for the synthesis, decomposition, purification, and compression processes. So going from hydrogen to whatever the compound is, for example, going from hydrogen to ammonia is the synthesis process, ammonia to hydrogen is the decomposition, purification processes, ammonia, mixed gas of nitrogen and hydrogen into pure hydrogen, and then compression at the end up to 20 bar. So you can see that the gas and liquid hydrogen have no purification or decomposition or compression requirements because they're already compressed and they're already pure, and then all of the other technologies do. So you can see for things like ammonia, methane, methanol, DME, which is dimethylethane, sorry, I might have mixed that up, formic acid and urea, they have quite high energy investments per kilogram of hydrogen stored. And some of that's because you have to, for example, with formic acid or urea, you separate CO2 and then you do further processes. And with urea, you separate CO2 and you make ammonia and then you make urea. So that means that for every kilo of hydrogen you're storing, you're actually investing, in urea's case, about 210 or 202 kilowatt hours per kilogram of hydrogen. So that's the state of those technologies. And so one of the other key things about storing and then transporting hydrogen is the actual hydrogen storage density. So this is a comparison of the real hydrogen storage density or the chemical storage density, and then the real hydrogen storage density, including the container of all of the materials. So all the further calculations of storage density have been done based on the lighter grey line rather than the darker line here, which is the chemical storage capacity. So in the technical assessment, one of the things that we did was the energy investment in kilowatt hours per kilogram hydrogen calculated based on the losses over time. So gas phase hydrogen and liquid phase hydrogen, liquid particularly has a high loss rate. It's estimated at about 1% per day. So for every day that you store it, you lose about 1%. When you do that in an energetic point of view, these are the energy investments per kilogram of hydrogen for the different technologies or the different storage methods. Sorry, I forgot to say earlier, there's only 16 here because the 5 that were highlighted on one of the previous slides, if you'd like to go back and have a look at it at some point, or I will go back and look at it. These 5 that are red, there wasn't enough information on them to do these further calculations. So there's only 16 going out from here. So even at really long storage times, like 1 year, the losses in liquid hydrogen per kilogram are less than the energy investment required for most of the chemical storage. The exception is in the carbons, MOFs, lanthanum nickel 5 and other low kinetic absorption technologies. They have quite low energy investments, and even their reversal is quite low. The energy investment required to reverse them is quite low too, so that's why they have low energy investment for storage even at long time frames. So on to the economic comparison. So for our assumptions, we included the energy cost of synthesis, transport, storage, losses, decomposition, purification, compression to 20 bar. We assumed an energy supply cost of, or electricity supply cost of 7 cents per kilowatt hour in Australian dollars. All the values were literature from the previous slide. The difference here is that we assumed we were going by sea to power an offshore station. And this particular boat was from a real boat that was a diesel boat, but we converted the power into a fuel cell using the same assumed power requirements for movement. So that comes out to 9.4 kilowatt hours per kilometre. And it's travelling 10 kilometres out to the offshore station, 10 kilometres back. The transport costs were taken from the Deutsche Bahn report on how efficient their transport was. I don't know if this boat is as efficient as this transport cost, but looking into other costs, they all seem to be about this number, which is about 0.025 kilowatt hours per tonne for sea-based transport. And once again, none of the initial costs or labour or insurance costs are included, and the return trip is included with reduced load in this case. So when we're delivering about 350 kilowatt hours per day in a fortnightly delivery of 4,900 kilowatt hours on a boat trip, you can see that the boat cost here is this little line down here. It's a pretty fixed cost. It doesn't matter. It's only dependent on the boat and how far you're going. The hydrogen delivery cost is the same for all of them because you have to deliver the same amount of hydrogen to get this much power. And the only difference is the synthesis and decomposition costs. And the compression costs are included in either the hydrogen delivery costs or the decomposition costs. So you can see the differences is largely the amount of energy required to make these different chemicals and how much power you need to put in that second process. So the low pressure carbon storage and the gas and liquid hydrogen come out much cheaper in terms of the energy cost just to do this one process. And assuming that all other things are equal, for example, your labor costs and insurance costs, etc., then these would be much cheaper. So then the next thing to consider is, this delivers 250 kilograms of hydrogen to get this much power, which is much less than this boat can actually carry. So what we did was do the calculation of a short distance export assumption using this same boat that has a maximum carrying capacity of 2 40-foot shipping containers, which it's up to 60 tons. And it can have, and included in that 60 tons or of those 60 tons, you can have a maximum of 110 meters cubed of storage. So using these loads, or these maximum loads of weights, and using 3 different electrical supply costs and all of these other things being the same, we calculated how much hydrogen and how much you could make by getting, or how much hydrogen you could put on the ship to start with. So in this is the weight and volume. So lighter gray is the weight you can put on the ship, or the maximum hydrogen you can put on by weight, and the maximum volume is the darker gray one. So whichever one is the lower one is the one that you can actually fit, because you're either over the maximum weight or over the maximum storage volume. So you can see for the carbons, these really low density hydrogen storage ones, you can't fit much hydrogen on the boat just because the amount of hydrogen, the density of hydrogen on it is very small. So when you do those calculations, we calculated the break-even cost for driving the boat from Hobart to Melbourne, Port of Melbourne, or vice versa. So 990 kilometres of transport, and the different electricity prices. So first one is 2 cents an hour, 2 cents a kilowatt hour, and then 7 cents a kilowatt hour, 11 cents a kilowatt hour. And when you do these calculations, you can see that the low density or the low pressure, low kinetic absorption materials come out quite well, as does the reversible liquid organic hydrocarbons, and gas and liquid hydrogen are once again the most effective. And then all of these other, basically all of the chemical storage methods are more expensive by quite a bit. So remembering that this doesn't include labor or insurance or anything else. So when you do those calculations, you can then work out how much power you can get out of the kilograms of hydrogen. And assuming a 50% efficiency on a fuel cell, you can, and these values of the 110 meters cubed and 55 tons, this is your return on energy investment for the 16 storage methods for hydrogen. So gas phase and liquid phase hydrogen are by far the most energy efficient processes, and then the liquid organic carbons and the reversible, low energy reversible hydrogen storage intermediates. And these more energy intensive processes of making chemicals for chemical storage are less efficient. So in summary, Gas and liquid phase hydrogen were consistently the lowest energy investment and highest return on, or energy return on investment. The low energy reversible carriers, solid state liquid carriers also had high energy return on investment. Lower infrastructure and processing costs mean that the low energy solar reversible carriers like carbons, the MOFs, lanthanum nickel 5 will probably end up having overall lower costs than methyl cyclohexane, toluene, and PDBT cycles, just because those both require catalyst decomposition processes and then purification afterwards. The liquid state and easier handleability of those things might make them more competitive in certain environments. The moderate energy solid state storage methods like the magnesium or the titanium alloy that we looked at in the study may have advantages because they can provide very high compressions, even though they require more energy to be able to do that and release the hydrogen. So some of these materials can compress hydrogen up to 5 to 7 to 1,000 bar, depending on the exact material and how many stages there are and that sort of thing. So other considerations for the chemicals containing hydrogen, such as ammonia or DME or urea, may actually make them more competitive. Things like formic acid can sell for between $500 and $1,000 a ton. So some of those things might actually be considered for small scale production. And the fixed energy cost of the transport and storage capacities affect the return on investment, return on energy investment or energy return on investment quite a lot, just because it costs you a certain amount to drive the boat, and it doesn't matter whether you have 1 kilo of hydrogen or 10 kilos of hydrogen or 500 kilos of hydrogen. The cost of those fixed or those fixed costs are actually quite important. And that's all I've got, and I don't know why that happens. There we go. Thank you very much, everyone.
Okay, thank you very much, Christina. Very detailed and intensive study of the economics, which I think are very important at this stage of the development of the whole industry. So now we're a little bit over time, but I could like to open up for questions. There are a couple of questions that have come through. I think most of them have actually been answered earlier, but a question from Peter Osman, and I presume is directed at you, Christina, is does this mean that a large number of small boats would be more energy efficient than a single large vessel for the same volumetric load carrying capacity? And if there are, if that's so, are there qualifiers that would discount that?
So it depends on the efficiency of the boats. Generally, a single large vessel with the same volumetric capacity should actually cost less energy to move than smaller boats. It really depends on the efficiency of the boat and also the efficiency of what's the word? It depends on how fast you want to go, if that makes sense.
Yeah.
Because the actual energy consumption, so energy consumption for anything that's moving is really related to how fast it goes. So if you have smaller boats that are going faster, they're less efficient than a large boat that's going slower, even if the large boat is less efficient. No, that sounds like it's talking in a circle. But unfortunately, like many of these things, it really depends on the details and really depend on the specifics of the circumstances. And that's one of the reasons why it's really hard to do these sorts of analysis without getting overly technical and detailed.
Yeah, got it. Yeah, good point. Understand that. There is one other question that's come through the chat screen for John, and I guess it's a general question that might be worth answering if you have a chance, John, is, are there any opportunities to propose new projects from universities, particularly those who are not current partners of the CRC, or can a non-partner be involved in any way with these existing projects? I guess you have a generic approach to that.
Yeah, thank you for the question, Ian. And so the Blue Economy is set up with its 40 participants, and all of those 40 participants are investing resources into the company to further its research. There are opportunities to join on projects, and that's sort of through two different routes. One route is on a project by project basis, and so if a project is developed where a third party actually is a really good match for a project, then we can look at including that research group, that university, or that company on a particular project. Alternatively, we can add additional participants to the Blue Economy CRC, but it's quite a complex process and would have to come with a really good value proposition for all of the participants currently in the Blue Economy CRC. So the short answer is yes, there are certainly opportunities to join in projects or into the broader community of the BAE CRC, but you're probably best off directing the question directly to me offline.
Okay, thanks, John. That's very good. And I think there's one more last question here before we close up and hand over to you again. It's so that the production of hydrogen at less than $2 a kilo, how much would it cost at the user end considering the energy losses during transportation? I suppose that's a question for a number of people and depends upon the situation. I'm assuming if we're talking about the marine environment, which this CRC is about, perhaps that question could go to Christina initially. Cost of production of hydrogen is $2 a kilo or less than. Does that include also energy losses during transportation?
So using 2 cents a kilowatt hour, you can deliver hydrogen for about $1.60, including all of the energy losses and storage and conversions and such. Okay. But that does not include any of the labor. So if you can do electricity for -2 cents and get paid to make hydrogen, things get better. But yeah, it's going to be quite tough to get it down to below $2. Just okay. Yeah.
But that's a good point. If you can get electricity at negative values, which is happening in Australia at different times of the year and different times of the day. So you never know, and it might be the case also offshore. It's hard to know. That's obviously a question for you, for Christina, to follow up on as the years progress.
Yes, indeed. Thank you.
All right, so I think we've exhausted our questions now. So I'd like to hand over to John again to end up with closing remarks.
Thank you, Ian, and thank you to all the presenters today. So I hope through this this brief webinar, you'll get to see that the Blue Economy CRC has commenced an active research program, and part of that program is certainly has a hydrogen focus. We have a number of research projects that are some of the scoping projects. We have about 17 that are currently reporting at the moment. Included in those is some of the work that we just had Christina describe to us. We've also got a number of major projects that are now underway as well, and some of those are in the hydrogen space. And Professor Gray has spoken a bit about some of the work that we're doing in that space. We're also in the process of acquiring some significant hydrogen infrastructure to support our R&D program, and Craig and Evan both alluded to that. And in the very near future, we'll be discussing a lot more the sort of what we've acquired and how we're going to be using that. But what we will be doing though is acquiring this infrastructure for the R&D program as outlined by Evan, but we also have a significant potential to produce commercial quantities of hydrogen. And so we'll also be looking at the opportunities for sort of offtake agreements for what we produce, both hydrogen and oxygen. As a number of presenters said, the oxygen produced is just as valuable to the agriculture sector as hydrogen might be in the future. We are still very early on in our journey, just over a year old, and so much of our work is on the sort of the front end of starting, but over the next 2 years I hope that we'll be able to continue these webinars and really show some significant progress in what we're trying to achieve. I'd just like to sort of also say that our next webinar is going to be titled something along the lines of how we grow salmon, and it'll be on the 20th of January in 2021. And that's a sort of a counterpoint to this. So we've spoken very heavily on energy today, but we are very much around promoting the blue economy, and that includes both aquaculture as well as offshore renewables and the like. So with that, I really thank you for joining. Stay connected with us through our website and through our social channels. And yes, 20th of January 2021, we'll be back in with our next webinar. Thank you, Ian.